Everybody say hi, Austin.
Hi, Austin.
We were going to just let you flounder, but Daniel looked out for you and asked if we were going to record it, so I guess we will. We're going to be talking about center of mass, and I'm going to give an English definition here that I'm going to translate into math in just a moment. The center of mass is going to be the weighted average of all positions of particles in a system. The weighted average of all positions of particles in a system. Now, this is computed slightly differently depending upon whether my system consists of discrete particles or continuous particles. When I say slightly, it's really actually all the same thing, but it just looks different, has a different form, and so our computations might go a different route here. Let me show you what I mean. Suppose I have a system of particles right here, and what I'm interested in is the center of mass, which is the weighted average of all positions of particles in the system. Choose an origin. Maybe M3 looks good. That was a good choice there because it allowed all your coordinates to be positive for your particles right here. So we begin by choosing an origin, 0, 0, and then we measure. And just for the fun of it, I'm going to assign actual numbers here, 3, 1, and let's go, the guy looks like -1, 4, something like that, and maybe M3 can be 5 kilograms, 3 kilograms, and 2 kilograms. I'm just making up these numbers. Now we're going to take the weighted average of all positions of particles in the system. And the positions are the 0, 0, the 3, 1, and the -1, 4, but we are going to weight those positions according to the masses that are associated with those positions. In other words, a mass of 5 kilograms gets 5 times as much weight as a mass of 1 kilogram. And so the way in which we do that is to add up the mass times the position, and here each mass is going to be the weighting factor for each one, and then divide that by the total mass in order to average it out. And this is what it looks like to do a weighted average of all positions of the particles in the case where you have a discrete system, a system of discrete particles. And so in this particular case, what we would do is to have just march down each one of the particles. So I get 2 times -1, 4 plus 3 times 3, 1 plus 5 times 0, 0. Now at first it seems kind of strange that we're going to do the 5 times 0, 0, because it seems like what we're doing is just zeroing out or negating the influence of the 5 kilogram object. But that influence shows up in 2 places. One of them in the top, but in the bottom, it also shows up in the total mass. So what that 5 is doing is diluting the effects of the other masses. And when we do, we get a vector quantity in the top, -2, 8, plus 9, 3. Over 1, which is going to be 7, 11. What did I do? Yeah, over 10. This quantity right here in the top, which is the sum of all masses times positions, is called the first moment of the total system. And that first moment is relative to the origin. And so what we're saying about this system is that relative to this origin, the first moment of the entire system is a positive quantity that points over 7 and up 11, or something like that. We'll have a little bit more to say about that. What units go with this? Well, yeah, that's right. Because we are multiplying by kilograms and dividing by kilograms, we are going to end up with units of position. Just like that. Now this raises an important question. This center of mass that we got right here was relative to our choice of origin. And we are fully aware that the choice of origin is up to the problem solver. It is arbitrary. So what would have happened if I had chosen a different center of mass? Well, before I do that, let's come back and look at where our center of mass is located. It's located at 0.7, so it's going to be over there and up by, did I do my math wrong? I did my math wrong. 1.1. Notice I caught that as soon as I started to try to visualize that center of mass. So over 0.7 and then up to 1.1. Here is the center of mass location. As we will discover when we do rotation, the center of mass is also at least on Earth, in a constant gravitational field, is the center of gravity. So I can treat the center of mass as the balance point for the object. If these objects were somehow connected like by a really light weight material, then I could put my finger on that material and balance the entire thing. And so that is the basis for, maybe you've seen some of the toys that are based on that, like the bird that can balance on its beak. And the way it does that is to cleverly have a lot of weight in its wings so that the center of mass is right at the beak. Just put your finger there, very good analysis. There's no problem. And actually, to go a little further, because the wings are down below the beak, that causes the center of mass to be a point of stable equilibrium. So that if you displace the bird a little bit, it just rocks. Okay, so this raises an important question, which is, what if I had chosen a different origin? Well, let's do that numerically real fast, and then we're going to do a fun. Let's rework this problem, but now we are going to choose this point to be our origin. And if we choose this point to be our origin, then relative to the original origin right here, the displacement vector for the original origin is +1, -4. I'm going to write that as with the angle brackets right there. And that is therefore going to displace all of these coordinates so that in our new coordinate system, this point is at 1, -4, and this point right here is at 4, -3. You can simply add the displacement vector as a translation on all the coordinates. Okay? Well, let's see what happens. If I compute the center of mass in our new coordinate system, then I get 2 times 0, 0, plus 5 times 1, -4, plus 3 times 4, -3, all over total mass, 10 kilograms, not 11, which gives me 5, -20, plus 12, 17, negative 29, 10. Boy, I'm in a hurry today. Which gives me 1.7 comma negative 2.9 meters. At first glance, this looks very distressing because it appears as if we got a different answer for our center of mass, which raises the really alarming possibility that the center of mass is not a well-defined quantity, but weight. Ah, that's right. We actually go and locate the center of mass in our new coordinate system. We observe that the new center of mass is equal to the old center of mass plus that exact displacement vector, 1, negative 4, that we had before. The physical location of our newly computed center of mass is exactly at the same point as the physical location of the old center of mass. The coordinates are different because we have a different origin. And that's it. We wonder if we got lucky here, so let's actually generalize it with a proof. Claim. Well, let's do it with Mars. I always forget. Relative to A, and relative to B, then my claim is that R prime is simply equal to R plus the vector that gets me from A to B. Wait, let me make sure I did it right. The vector that gets me from B to A. And the proof is relatively simple. When I measure R prime COM, all of these coordinates R prime are equal to the original coordinates Ri plus the translation vector that gets you from the new origin to the old origin. But now we believe in the distributive property. So we can distribute our mi, and we observe that the vector BA is a constant. So that we can pull it out of the sum and our masses cancel. And this first quantity right here is exactly the original RCOM plus BA. Yep. What's the upshot of this? That no matter what origin you pick, your center of mass will always have the same physical location. It will simply have different coordinates that reflect the choice of origin. Now, you said you had a question about number 48?
Yes.
All right, let's take a look. Go ahead. I don't have my book in front of me.
Is
Ah, a uniform piece of sheet metal is shaped as shown. Compute the x and y coordinates at the center of the mass of the piece.
And then I realized I did wrong, so I just fixed it.
In the green.
No, no, I didn't do that.
Oh, really?
Yeah. I did just wait to fix it. I was like, I'll do it when I.
It will be where you can actually make
Is this correct?
yes, it's
What's up? Okay. Very good. Alright. Now, I'm not even sure if they tell us the masses of the pieces, and it turns out it doesn't matter. We can call each piece of a mass M. And we're going to use symmetry to assert that all the pieces have equal masses to them. And what is the width and height of each piece?
10. The bottom one,
Uh-huh.
the height is 10, width is 30. So they all go by 10.
Each piece is 10. 10 by 10, sort of.
Oh,
Yeah?
I thought
Okay.
you meant that.
Yep. So now we are going to pick an origin for ourselves. And I think the cleverest origin to pick is probably this bottom left corner right here, bottom left, center of the bottom left piece right here. Because when I pick that center, now each of these centers is going to be 10 away from its fellow. And likewise here. So we can go through and we can mark coordinates 0, 0, 10, 0, 20, 0, 0, 10, 0, 20, and 10, 20. Just like that. And now we can pull off a weighted average of coordinates. Our COM is going to be m times 0, 0, plus m times n0, plus m times 20 times 0, plus m times. This is kind of a pain in the neck, but it's not horrible. And all of that over 1, 2, 3, 4, 5, 6 m's. Well, the first thing to observe is that all the m's cancel out, so we can ignore those. And now we just march through and add up all the x's, and then add up all the y's. We get 0 plus 10 plus 20 is 30, 30, 40, comma, 0 plus 0 plus 0 plus 10 plus 20 plus 20 is 50. And all of that over 6. And when the dust settles, we end up with 20 over 3, that's going to be 6.7, comma, 8.3, yep. Okay. And that M unfortunately looks like the mass M, but it's not, it's meters. When we're done, let's do a little reflection on what we discovered. And what we discovered is that the center of mass is located, let's see here, if this origin is 0, 0, then 6.7 is going to be a little bit beyond the edge of the first square there, and 8.3 is going to be somewhat substantially beyond the edge, so that our center of mass is located right here, outside of the feet section. So the key to making this a relatively easy problem was to choose a good origin, and then to assign coordinates to all the pieces. What I'd like to do now is to consider what happens if our object is not made of discrete pieces, but instead is what we would call a continuous object, or an extended object. And let me speak very generally here. So let's imagine that I've got an object here that is made out of some material. And it's ugly. And there it is. So the question then is, how would we go about finding the center of mass of this object? Well, again, we're going to choose for ourselves an origin. Let's imagine that we choose an origin right here, which is not necessarily the best choice, but there it is. I'm just choosing it out there to get it out of the way of what we're about to do. And now imagine that we are going to estimate the center of mass by pretending that it is a discrete object. And what that would amount to is taking and dividing up our object into very small chunks. And we're going to choose rectangular chunks. A few of those rectangular chunks are going to end up overlapping the boundaries of the object a little bit. So we'll have a little bit of error, but it's not too bad. And each one of our chunks is going to have a width that is a small piece of x dx. And it is going to have a height that is a small piece of y dy. And now what I'm going to do is to march through and add up all of the pieces. So I'm going to do x's and y's separate here. So that the x component of the center of mass is simply the sum of all of that right there. Okay. What this does is it gives me an estimate. And now, if I take and let the size of dx and the size of dy go to 0, then what I get is an integral from my sum. So this is an approximation idea. But if I take the limit as the size of my delta x's goes to 0, then I get the integral of xi of x times. Now, what happens to my masses? Here's where this gets really interesting. If I consider a little piece dx and dy, then the mass that we have here is going to be an infinitesimally small piece of mass dm. And it is that infinitesimally small piece of mass dm that we are multiplying by the position. If I take a representative element out here somewhere and call that dm, and it has a position vector relative to the origin r, x, y, like that, then what I'm really doing is adding up x times dm. And I am dividing by the total mass, which is the sum of all of the pieces dm. So the way to read this is we are doing a weighted average of positions, and the positions are being weighted by the little pieces of mass dm and being averaged out by dividing by the total mass, which is the integral of dm. This quantity in the top is called the first moment, but only in the x direction. And the y center of mass, likewise, is going to be the moment of y direction divided by the total mass. Now this is kind of weird. We've never integrated with respect to mass before. So how does that actually work out? In practice, the way it's going to work out is this. We're going to take this dm, and we're going to represent the dm in terms of dx and in terms of dy. And we're going to do that by the use of density. Let's do a really simple example. One that we already know how to solve. center of mass of a uniform rod of length L and mass M. Now, we don't need calculus. Calculus is a high-powered tool to solve this problem. You can probably give me the answer to this question without even working too hard. Just by using an appeal to symmetry, where does that center of mass have to be located? Yeah, it has to be located at the center of the rod. So we're not using calculus to solve this problem because we need it. We're using calculus to solve this problem because we need to practice the calculus problem to see how it's going to work out in a simple situation. Okay. First, I observe that the center of mass really is only in one dimension, so we only need to worry about x's in this particular case. And the second thing that we observe is that we need an origin, and so I'm going to pick the origin to be right here. If I pick the origin to be right here, then the end of the rod is out at L. Now comes the integration part. And to set up the integration part, I'm going to subdivide that rod into lots of little tiny pieces dm. Here is one of them. This is a representative piece dm. And I'm going to add up the positions times masses for all of these pieces dm in order to get the total moment. And then I'm going to divide that by the total mass of the rod. Well, how do I accomplish that? Notice that if this piece dm is representative, then it is at an unknown location x, measured relative to the origin right there. And notice also that we get dm by taking and chopping up this rod into lots of equal pieces. So the logic is that each piece is going to be equal to, essentially, or proportional to, the length of that piece times the density, the way that the mass is distributed along the entire rod. We can call that density lambda, if you want, the linear density. And the linear density is the entire mass divided by the entire length. And what it tells us is how many kilograms there are per meter of rod. So that if I now multiply lambda times dx, then I'm taking a certain number of kilograms per meter and I'm multiplying it by a certain number of meters, a really small number of meters, to get a very small mass in kilograms of that little piece of the rod. This is saying, it's essentially a proportion. This is saying that dm is to dx, just like mass is to length, because the mass is uniformly distributed. Does that make sense to everybody? Well, this now gives me the key to unlocking the whole thing, because I can say that the integral of x dm is simply the integral from x equals 0 to x equals L of x times lambda dx. Now, the lambda is a constant, so I can pull it to the outside. And I get this integral right here. And this computes the moment in the x direction of that rod. Let's keep on going. The integral from 0 to L of x dx is x squared over 2, taking it from 0 to L, which gives me m over L, that's all squared over 2, ml over 2. And now, the center of mass is moment divided by total mass, which is equal to ml over 2 divided by mass, which gives me L over 2 as that mass. Interesting. I think we need to see it a couple more times before comfortable.
could you have different lambdas in like different directions? Like
You could, right, so we would call a material like that anisotropic. It is different in one dimension, its properties are different in one dimension than it is in others. But you could also have it if your object is not uniformly shaped. So let me, I'm going to illustrate that in just a minute. Let's consider now the center of mass of a rectangle that is uniform. Of dimensions A and B. Okay? So the first thing to understand is that the x's and the y's are independent of each other so that we can march through and do all the x's separately and all the y's separately. So let's consider the x's first. If I do the x's first, it's helpful to set up the integral expression first and then come back and fill in the details. So I'm going to say that the center of mass in the x direction is the integral of x dm over the integral of dm, which is the total mass. Now, the total mass, let's just make up a number for it. Let's call it n. Now, because I'm operating in the x direction, what I'm going to do is to march down in the x direction. And I am going to take pieces in the x direction. And to do pieces in the x direction, that means that I need to split up my rectangle into vertical strips that are all sitting at location x, right here. So this is my basic setup. Now we're going to ask the important question, what is the mass of my vertical strip? And the mass of my vertical strip should be the area of that vertical strip times the density, the distribution of mass for the entire thing. And on the assumption that this is a uniform rectangle, the density, let's call that density, well, sigma is often used for area density, but let's just call the density density. And is equal to the total mass of the rectangle divided by the total area of the rectangle, which is infinite space. And therefore, the mass of my representative strip right here is equal to the area of that strip times that density. So the area of the strip is height times width, which is going to be d times dx, times the density, which is m over ab. The b's cancel out, which is kind of interesting. And so I get m over a times dx as the value of dm. And this allows me now to substitute here so that xcon is going to be equal to the integral of x times m over a dx. And my limits of integration are going to be taken from the first x to the last x, which is 0 to a. Just like that. Out comes the constant m over a. And the integral of x dx is x squared over 2. So that I get m over a times a squared over 2. There we go. I forgot to divide by the total mass. That's which is equal to over 2 when the dust settles. So that, unsurprisingly, the center of mass in the x direction is in the middle of the center of the rectangle. Right, that's the million-dollar question. dm in all cases is going to be found by as density times area, length, volume, whatever dimension you're working with. Yes. Yes, that's right. And in the case of an isotropic material, one where the density is uniform, then it's just total mass divided by total length, area, volume, whatever you're working with. If you have an anisotropic material, then your density will have to be given or calculated somehow. Well, the same kind of consideration happens in the y direction. Here's a rectangle. We have A, B, but now because I'm going in the y direction, we are going to take and split up our object into horizontal strips that have a height of dy that are located at the location y, like that. Notice that what I'm doing to get these various strips is I'm taking all of the points that reside at a single location y. And in the other case, I took all of the points that resided at a single location x. And so I can say that my density is equal to mass over area, again, same density as before. My dm now is going to be equal to density times density times area. And the area of my strip right here is length A times height dy. Which gives me m over b times dy. So that now, the center of mass in the y direction is the integral of y dm over total mass. And now I can go through and replace. dm is equal to m over b times dy. And my limits of integration are from y equals 0 all the way up to y equals b. Out comes the constant m over b. And I drop my over m in. So that I get y squared over 2 from 0 to b. Masses cancel. And unsurprisingly, I find that the center of mass in the y direction is also in the center of the rectangle. Okay, we're going to practice this some more tomorrow with other objects, but before we do, I want to, before we call it quits, I want to consider or do a little bit of a look ahead to see what that might look like if we have a strangely shaped or strangely density object. Let's consider problem number. Where did we go? Yes, problem number 49. A rod of length 30 centimeters has a linear density given by lambda equals, is it 20 plus 50x? 50 plus 20x, where x is measured from the left end?
It just is one end, so.
Measured from the end. Now they want to know where is the center of mass. Now, there are a couple of different ways that this linear density could come about. It could come about because my rod is made out of different materials as you go down, unlikely. More likely that the rod simply gets larger as you go down. For example, Harry Potter's wand, something like that, right? So that at one end, it's thinner and it has a lighter density, and as you move down, it gets thicker, and therefore it has a larger density relative to x. So we're going to begin by saying that the center of mass is equal to the integral of x dm over the total mass, like so. To get that total mass, we're actually going to have to integrate dm to make it happen, because they don't tell us the total mass here. Okay. Now, to get the dm, we're going to walk through and chop up our rod into lots of little pieces dm, right? And we're going to take dm to be equal to the density times the thickness of that piece. And since the density is given to us, then we can pull off an immediate substitution. And lo and behold, we have our dm. So that the whole thing now becomes the integral of x times dm over the integral of dm. What about the limits of integration? They're going to be from the first x to the last x. And if this is x equals 0, then this is x equals 0.30. Everything's done in meters, am I correct?
Yes.
Yeah. So we're going to be integrating from 0 to 0.3 and from 0 to 0.3. And the actual integration here is relatively simple. You guys can do the distributing, power rule, blah, blah, blah. So we'll go back and finish out this problem tomorrow and also take a look at a situation where you have a triangle.